Okay, let's take a look at what's going to be on the final exam. As you saw, there are quite a few slides we could be taking a look at, but the reassurance is that if it's on the slides, it has a potential to be on the test. If it's not on the slides, don't worry about it. So, I'm not going to look for page 44, bottom paragraph, and ask you a question about that. I'll be asking specifically questions about what's in the slide deck. First thing we did was we learned how to count all over again. Start from scratch. Brand new. So what we looked at was the decimal system that we all have some degree of familiarity with. Then we added binary to it, and we found out that 0 was still 0. But it's either 0 or 1. 2 is a 1, 0, and we counted all the way to 1, 1, 1, 1 as the highest we can count with 4 bits. Then we went over and figured out how to count in what's called hexadecimal, or base 16. And we found out that after 9, we still had to keep it to a single digit, so we had to use other symbols to get 10, 11, 12, 13, 14, and 15. So we used A, B, C, D, E, and an F. Any questions regarding where we started? All makes sense.
Yeah.
That's scary, isn't it?
Yeah, at first I was like, what?
We also looked at how easy it was to go between hex and binary. If I take a number in hex, 9F2, spread it out, 9F and 2, and each one of these becomes a 4-bit binary value. So 2, 0, 0, 1, 0, F, 1, 1, 1, 1, 9, 1, 0, 0, 1. When we put it all together again, we saw 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, which is the conversion from hex to binary. Now, for your purposes, take a quick look at BA6, and I want you at your desks to do that conversion and see if you agree that that's the right answer. So what do you think? Does it work?
Yes. Yeah.
Sure.
Yep.
1011 is a B, 1010 is an A, 0110 is a 6. So we know it works. What was that?
What was the conversion from hexadecimal to decimal again?
Hexadecimal to decimal is basically divide the decimal number by 16
Yeah.
and come up with numbers, or look at, let's flip over to the document camera.
So you, in that case, you would turn the A or B into the actual.
Sure. If we go back the other way just a moment, let's take 15F. We'll take 15F to decimal. Are you ready to do that one? So the same way as we move from binary, we take f times 16 to the 0. That'll get us a 15. 5 times 16 will get us an 80. Sixteen squared is going to be what? A number you ought to know off the top of your heads.
No, I don't.
Can you zoom in on that just a little bit?
Well, no, I'm serious. I was like, wait. I recognize that number. It's visible by 8, so. Okay, so you do actually, I was thinking that, okay. So it's almost like the opposite of base 2, but you're
It's the same as base 2, but you're multiplying based on a multiplying or dividing based on a 16
Yeah,
rather than based on a 2.
exactly.
Okay?
Thank you. That makes sense.
Something else we looked at, binary coded decimal. And this came back when we started going through adders at the last encounters at the end of the semester. We got into BCD count again.
Yeah, Pat.
So what's BCD count? We've got the numbers. We've got any number 0 through 9. In decimal. So if we've got a 954, binary coded decimal is going to take the 4 and make it a, how many bits?
4.
A 4-bit value. And there's the binary coded decimal that comes out of it.
I think you meant just regular decimal, binary decimal.
And to get from binary coded decimal back to decimal, it's going to be just the opposite. You look at the binary number in 4-bit chunks and convert it to its equivalent decimal value.
Just out of curiosity, did you have another set of 4-bit if there was another number?
Sure.
I know that sounds simple, but stupid.
We can go.
question, but-
We can take this and stretch it as far as we want.
Yeah, as long as, yeah, as much use as you need to send the data.
Mm-hmm. Mm-hmm. So here was an example. We just showed it on paper also. We're going to take a binary coded, and this is actually the way you wanted to go the other way. Take this number, break it into its 4-bit equivalents, and we see that the last 1001 is a 9, 0011 is a 3, 1000 is an 8, and 0110 is a 6. So you've just converted a binary value back to its decimal equivalent.
That's probably the simplest.
Now, what was the problem that this one showed out? We talked about it before, and it was on the test.
The extra 4-bit in there?
What is the decimal value of 1100?
12.
Can you write that in one decimal character?
No, it's
No.
not.
Therefore, this is an illegal value.
Yeah. I think they use
So that's binary coded decimal.
the
Gray code is used, you saw equivalent of it almost in the ring counter, but this is used in particularly rotary applications where there's only one bit that changes from each value to the next. So where we would normally count 000, 001, 010 to get to a 2, we can't do it that way because this one changes. This column changes, the B1 column changes, the B0 column changes. So we have to have a different code. The code we use is 000000001. Okay. Now we're going to change the gray code first column. So it's 011. We've only changed one bit between row 2 and row 3. Then we get to row 4, 010. Again, we've only changed one bit. So that's the value for the 3. Then we're going to change one more, but here we'll go to the outside, 110. We're only changing the gray code second column, and we're defining that as the equivalent to a 100 or 4. Then we go back to the next one and go 111. Well, we're not ready for 7 yet, but that's changing the G0 column. And we change the G1 column, 101. And then finally, our 8 is a 100. What makes that valuable if I'm doing this over and over and over again? What is the next number in the sequence here?
101.
We're going back to 0. And we're going to erase this 1 and make it a 0. And we've come right back to the beginning of the cycle again.
So you're just more limited. Like,
I wouldn't say more limited. I'm using a 3-bit system in order to watch a repeating function and know where I am on that repeating function.
like a test, like a little tester.
Or you could run this inside a motor and know what the position of a cam is by what the code is when the writer comes past the reading field. So we learned how to count again. Then we went in and started looking at gates. First one we looked at was an OR gate. OR gate looks kind of curved on the base, comes to a point at the far end with curved lines. If we have two inputs, A and B, the output is X is equal to A or B. And here's the truth table. 0, 0 is going to get a 0 or a 1, I'm going to get a 1. A 1 or a 0, I get a 1. A 1 or a 1, I get a 1.
So basically saying A or B has to be 1 for it to be 1.
If A or B is 1, I'm going to get a 1 out.
Yeah. I did
And
that
that's the whole
better
concept of
now.
an OR gate. Huh?
I did that better now. I know it's the simplest thing, but
Yeah. Then we went on from OR gates to AND gates. OR is the equivalent of addition. Or 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. That's where we messed up the addition process, but it follows from the logic here. The AND gate is equivalent to multiplication. So A and B and C. X equals A and B and C. This is not just multiplication. This is the AND operation. So A and B A is 0, B is 0, A and B is a 0. A times B is a 0.
Yeah.
A 0 and a 1. A 0 times 1 is a 0. 1 and 0. Well, 1 times 0 is a 0. But 1 times 1 is a 1. Here's the symbol. We say that the output X is equal to AB. Questions? Next operation we looked at is the NOT operation. I can do it either with a bar over the top, that's X equals not A. Here I'm showing an equivalence that if I use an apostrophe, A apostrophe is the same as A with a bar over it. And you saw all semester that you couldn't predict for certain what symbol I was going to use because I moved back and forth. And you can too.
Is there a keystroke combination that gives you this overbar?
Yeah, that's a good point.
There probably, I won't say probably, there is one, but I use a Mac, you're using Windows.
Yeah.
You would have to do a lookup on the web to find the overbar symbol.
I think there's like an insert symbol button that gets it.
Yeah, that's very
Yeah. The other thing you can do is open your equation editor and take 10 minutes to figure out how to write this equation and use the overbar that's built into the equation editor.
On my notes, I just use an underline and I just know that it's
I use the apostrophe.
because that apostrophe is kind of hard to see sometimes.
If you're writing small, it looks like a dot on the page.
Yeah, pretty much.
But A is equal to 0, that means not A is equal to 1. A is equal to 1, then not A is equal to 0. Again, a very straightforward truth table. As a device, we did the basic buffer with a not on it. So we come into this as A, the circle says make that a not A. And there's our result. If we're looking at the output of a gate, if the inverter operation, if A is equal to 0, and then here it goes to a 1, and back to a 0, back to 1, back to 0, the not A is going to be just the opposite. Or we could say it the opposite way. If X is equal to 1, and then drop down to 0, come back up, drop down to 0, come back up, then A, which is not X, is going to be just the mirror image of the waveform. So how do we use it? We had to think about how this worked for a minute, but with the switch open, the input's tied to ground, so I've got a 0 here. 0 here means what do I have as the output? A 1. When I close the switch, what do I have at the input?
1.
I have a 1 at the input. Invert it, I get a 0 at the output. What was that?
Oh, I just got what the resistor and ground did. It made it 0.
Yeah, the resistor is tying this pin to ground.
Yeah. So
And that's how we did with our switches too when we started building schematics.
What makes it difficult to understand is that the button shows open, not press, but they start off with saying it's pressed.
Okay, if you read the note with it, the logic level 1 is true when pressed. It's false when the button is not pressed.
Correct, but the text.
Yeah, the text
itself
is not
shouldn't ask
necessarily-
the position of the button. Like it should say not pressed, and then on the other side pressed, because that's.
I could almost take this out and this out, and it would be more obvious.
Yeah. Like, for these inverters, where exactly does like the power come from if it's not pressed? Is it like the chip?
Okay,
Your power?
good question. Let's go over to the dot cam. So I'm showing going down one side where pin 1 is the input to the inverter and pin 2 is the output, and so on. So far, so good. On the other side, pin 8 is going to be the input. We go to the inverter, and pin 9 is the output. Pin 10 is the input. To pin 11, or pin 10 is the input to 11 is the output, then 12 and 13. But then I've got pin 14 over here. And pin 14 is always VCC, 5 volts, and pin 7 is ground. And that's where the power comes from to drive the gates. The circuitry on the board uses the power and ground pins in order to do their operation. Does that answer the question?
Yeah, basically inside it looks exactly how it was in the diagram.
Inside is performing these functions, but it's using all sorts of other transistor and diode type logic.
That is not belong to this class.
Say again?
I don't think so. That's really hard. It's not belong to this class. That's right.
The only thing that belongs in this class is the VCC and ground.
Right.
We're not going to shave the top off the chip and start looking at the parts inside the chip.
So much. Yeah, that's beyond that.
At the end of the day, we gotta know how much.
That isn't even going to be accomplished in any of the classes you take.
This is just
Yeah.
a surface.
You just gotta know how to use them.
Exactly.
So it's just the pin chip with the ground and you call it the other one.
Oh, do you see those surfaces?
Ground and plus.
Yeah. So you see
Ground and plus.
Plus.
Plus V.
Oh, plus we the 5 volt plus.
Mhm.
Or, yeah, or power supply.
So if we get into this and start looking at how do we take gates and put them together for A and B, or A, B, and C, and so on, we can start with A. We invert A so that the input to the OR gate is an A naught. B just comes straight in. So the output of this OR gate, recognizing the OR, is A naught or B. A similar but completely different operation is performed if I reverse the gates. If I take an OR here, A or B, I get A or B out. But then if I invert, now I've got A or B, the whole expression inverted. Again, follow the gates. Follow them in order. Logic circuits. We looked at this in order to say, okay, I've got 4 inputs, A, B, C, and D. Now, depending on the question, I can say, what is the output of this circuit? Or I can go backwards and I can say, given this output, what do the input gates look like? If I give you this as the answer and say, what was the question, then you're going to work from right to left. But given this, if I have not told you what this is, then you're going to start on the left. A becomes A naught, B comes straight in, C comes straight in, so the output of the AND gate is A naught BC. The second gate, A or D, so I've got an A or D. Now I go through an inverter and I've got A or D, the expression inverted, so it's A or D naught. Then I feed both of those expressions into an AND gate and I get A naught BC from the top line, ANDed against A or D naught, and I've got to have the whole expression here. So that's moving left to right. You can go either way, you have gone either way. Another example, same thing. What is the output? I've got A or B, so this is A or B. A or B and C. Notice the combining with an AND, but keeping the A or B as the input separate from the C. Now I'm going to invert it. So now I've got A or B and C, the whole thing inverted, and that goes into an OR gate. That OR gate has D coming in on the other line. So the first line in gives me this expression, ORing it against D. Then I bring E in on an AND gate. And I've got this whole expression multiplied or ANDed against E. I could have given you this expression and said, okay, take it back to the inputs. Let's go back over here a minute. So if I've got this expression, how do I work backwards? I'm going to go to the output. This is the final output. And I notice that I've got this term ORed against E. I'm sorry, ANDed against E. So I've got A here, or E here. Take it backwards. Let's get rid of the not with a quick inversion. And I've got A or B and C, but I've taken care of the not expression. Now we go back another step, and this is extremely similar looking to an AND gate. Oh, I left one term out. A, B,
You missed the OR gate
right here.
in front of the inverter. There you go. And on the other side. On the dot side.
Oh, you got D right there.
Yeah. There you go.
There it is.
It gets tricky.
Are you using an inverter?
That's not very pretty, but it's accurate.
So like if on the chest and grip, something like if it's just sloppy, but like something like that, it will get that full credit there.
If you drew it the messed up way I drew it, you get full credit. If you left out the OR gate, you would not get all the points.
Wouldn't you have to
Oh,
turn,
flip the orbit.
wouldn't you have
So
to
you have to
turn
do it
the A
exactly.
into an A naught from the very beginning?
So it doesn't matter if it's hard to do it.
Well, there was no A naught at the very beginning. This naught was dealt with here.
I was looking at the A naught you have. Oh, that's just the parentheses.
Yeah.
Okay.
You have to get all that A, B, C before you invert it.
Yeah.
Okay?
Yeah.
Now, a system like this is often easier fixed by breaking it into its parts. If I want to know what combination of A, B, and C I need to put into this, then what I'm going to do is I'm going to look at my three inputs, A, B, and C, and look at how they transfer to the next stage. So I've got two stages at the second level. The first is A naught and B. The second one is B and C. So if I start with my ABC and count from 0, 0, 0 all the way up to 1, 1, 1, then I know that A naught, which is going to be the output of this stage, is going to be the opposite of A. So where A is 0, A naught is 1. Where A is 1, A naught is 0. Then I'll go to the next column and I'll say, okay, I've got A naught and B. So what do I have here? A naught and B. A naught and B. This one and this one, the orange ones.
Yeah.
A naught and B still is 0, 0, 1, 1. So I'll get a 1 here. And a 1 and a 1 is a 1. 0 and a 0 is a 0. 0 and a 0 is a 0. 1 and a 0 is a 0. 1 and a 0 is still a 0. So now I've solved this one, A naught B, which is this leg of the circuit. So then we'll go to the next leg of the circuit. We want to look at BC. So this is the orange ones here. When are B and C both 1s? I've got both 1s here, so I got a 1 here. I've got both 1s here, so I've got a 1 here. All the rest of these are 0s. So only B and C is only 1 when both B and C are 1s. That happens twice. The last question we've got is, okay, what is, if V is equal to A naught B, that's this column, and C W is equal to B and C. So I go to B and C, and I go to A naught B, and I put those two together. This is an OR, so if this is a 1, or if this is a 1, I'm going to get a 1 out. So in this case, A naught B is a 0, BC is a 0, so I get a 0. Another 0, 0. But in the third row, A naught B is a 1. BC is a 1, so BC and A naught B gives me a 1. Following it down further, because we're dealing with ORs, 0 or 0 is a 0, 0 0 is a 0, 0 or 1 is a 1. And we've got to remember we're dealing with an OR gate here. So this 1 or 0 is a 1, 1 or 1 is a 1, 0 or 1 is a 1. So from these inputs, I only get an output of a 1 when A is 0, B is 1, C is 0, or if A is 0, B is 1, C is 1, or if all three of them are 1s. Those are the only times I'm going to get the output I'm looking for. we get the same thing available here. First, we're going to go through. A goes to A naught, B and C, so I got an A naught, B, C. The OR gate here is A or D, but I feed that into an inverter, so now I have A or D naught, A naught, B, C into an AND gate, so what's the answer? To solve this one, you basically are going to go through exactly the same process, looking at the A naught B C, when is it a 1? A or D, when's it a 1? A or D naught is the inverse of A or D, so we'll figure out when this is a 1. And now we'll AND it together so that I have to have a 1 in this column, and I have to have a 1 in this column. The only times that happens are when I get a 0, 1, 1, 0 as the input. I get a 1 here and a 1 here, so I get a 1 out. And that's it.
Wait, so on ours, we just drag the blue box so we can see it.
I dragged the blue box. But you're going to be able to, you'll have access to this video afterwards, assuming it works. Which I believe it will. So here we talked about implementing circuits from Boolean expressions. We got AC or BC naught or A naught BC. And these are 3 input OR gate. But we can look at this and we can take it the other way, and we've got 3 terms ORed together. We could take this back, have an A and a C with an AND gate. We get a B and a C naught. We could have an A naught and a B and a C. So we could take this back and add additional gates, if that's what the question was. So your challenge is to draw the whole circuit, and I'll let you work on that at a later date, but this is what it looks like. So you can follow it from the output back through each of the terms to the output OR gate, then back to the AND gates that create the combined terms, and then add the inverters in the appropriate places to get the C naught term here, to get the A naught term here. And you start with a clean ABC, and you end up with this expression at the output. Here's an equivalent one. A or B ANDed against B naught or C. Here's the circuit you're going to come up with. Now I'm setting this up with the question, then the answer without going through it all, because this is something you can walk yourself through and prove after class is over. Hopefully you do it before the final exam. It's also feasible to look at this in terms of, if I know A and B over time and create a waveform for A, synchronously a waveform for B, under what occasions am I going to get X equals AB naught? A, B, in this case, if A is anything, if A and B are not simultaneously 1s, I'm not going to get a 0 out. If A is a 0, I'm going to get a 1 out. If B is a 0, I'm going to get a 1 out. So if A is a 0, I get a 1 out. B is a 0, I get a 1 out. Here's A is a 1, B is a 0, I get a 1 out. So when do I get a 0 out? Only when both of them are 1s. So I look across here. These are both 1s. Don't have both 1s here, but when both of these are 1s, then my output goes to 0. This whole stretch, this is a 1, but this is a 0, so it's a 1 out. You get a 1, gives me the 0 out. 0, 1, well that's a 1 out. 1 and 1 gets me the 0 out. And there's the final waveform. So I can anticipate in advance what this waveform is going to look at if I know what the input waveform looks like. Questions? And you actually began to see this as we built the counters, and you were looking at when were the J and K high, when were the Q and Q not high. You were following that waveform. I'm going to look at the Boolean theorems for just a moment, and then we're going to pause and let you take a break, get some fresh air, and we'll pick it up from there. The first theorem, anything ended against 0 is what? 0. Equivalently, anything ended against 1 is whatever that input is, because a 1 is always a 1 out. Third one, x ended against itself, it's going to be x out. That's fairly intuitive. Anything against its complement, x and not x, one of those two terms is a 0. 0 into an AND gate gets me a 0 out. A or 0 is going to get A, because 0 has no impact on an OR gate. X or X, oh, that's going to be an X out. If we look at X or 1, the 1 overrides, so I'm going to get a 1 out. This next one, X or not X, if X is a 0, not X is a 1. If X is a 1, not X is a 0. In either case, I've got a 1 to an OR gate. That's going to get me an OR out. If you've got a problem like this, draw the truth table. These are theorems you can memorize, and you can trust them, take them to the bank. But if you're not sure, draw the truth table. Work out the truth table. Going back to high school, commutative law, associative law, distributive law. They worked in high school algebra, they work in Boolean algebra. X or Y is the same as Y or X. X and Y is the same as Y and X. X or the quantity Y or Z is the same as X or Y or Z. And I can get rid of the parentheses and just say, okay, it's the same as X or Y or Z. Same thing with the AND function. X and YZ is the same as XY and Z is the same as XYZ. Distributive law is a little bit more challenging. X ANDed against Y or Z, first times the first, or the term times the first, plus the term times the second, so I got XY or XZ. We can spread it out into 4 terms, Y or X ANDed against Y or Z, Y, W times Y, W and Y or W and Z, or X and Y, or X and Z. There's multiply out terms that we learned years ago. These get a little bit more challenging. You got to think them through. Also, watch the overbar on this slide. It can mislead you if you're not careful. First one is X or XY. We're saying that equals X. Build a truth table. Convince yourself of that. If X is a 1, then I've got a 1 out. If X is a 0, then XY is still a 0. X is a 0, so I've still got X out. So whatever X is, I follow. The next one, X or X not Y. If X is a 1, I'm going to get a 1 out. If X is a 0, X not Y becomes Y. So it's X or Y for X or XY. Or, excuse me, X or X not Y. Similar kind of thing if I move what the inversion is. X naught or XY. If X is a 0, that's a 1, so I'll get a 1 out. If X is a 0, X is a 0, it cancels this one. But if X is a 1, this cancels. This is a 0 or 1 times Y, and I got X naught or Y as the output. Again, if you've got any questions at all, build the truth table. Question?
So, this is basically absorption. So, wherever it's going to end up being equal to, like, so for instance, like X plus X naught Y is equal to X plus Y. Since it was X in the front, that's why it ended up being X
Which one?
plus Y.
14, 15A, or 15B?
15A.
Okay, X or X not Y.
Since the X is before the X naught, that's why it becomes X and not X naught.
Now, I'm just saying that these are the two terms that I'm comparing.
Yeah.
If I've got an equation I'm dealing with, and I end up with an X or XY, then X or Y is the simplification of this.
Yeah, I'm just trying to figure out how the answer ended up being X plus Y and not like X naught plus Y.
Build the truth table.
This actually refers to the table.
If X is a 0, then X is a 0 and X naught is a 1.
Yes.
I'll come to you in just a
So
moment.
for one of these questions, can you like show us like what truth table do you want us to draw for like these specific questions?
If you were trying to solve this one yourself,
Like how do you want us to draw the truth table?
or how do I want you to draw the two any way you want so you get the right answer.
Oh.
But what I would look at, let's take the second one.
18A.
So I got X or XY, or X not Y. Now let's do the second column as X not Y.
Yeah.
That's going to be the starting point. Now I'm going to look at the second term, X not Y. X has to be a 0 to get this to be a 1, and Y has to be a 1. So to get a 0 here and a 1, going to get a 1 here, right? That's the X not Y. From this, I know that X not Y here is a 0, X not Y here is a 0, X not Y here is a 0. So looking at the last column, when x is a 1, it happens twice. I don't care what y is. If x is a 1, then I'm going to get an output. X not y only has an output here, and that becomes the table I draw. When I look back at it, I can see that these terms are whatever x is, and that these terms are whatever y is, but I've already got a 1 here. So that's how I move from the truth table to the solution.
Is that drawing right there, right, plus x, y, what is that? Is that 0?
Where?
Oh, that drawing right there, left.
So you're-
Oh, here?
Yeah.
That's just the.
It's me crossing out something.
Oh, it's x, not y.
Okay, since the one's already there, that's why it absorbs it.
Yeah.
Okay.
If you draw another line to do the x plus y, the answer of the x plus y is going to be exact same thing.
Say that again, Hamid.
If you draw one more line at the end and put the x plus y, the answer of the x plus y is equal to whatever you just.
Okay, x or xy. These two are true because of x. These two are true because of y. So it's x or y. Is going to get me a 1. The only time I've got 0, 0 is when x and y are both zeros.
That's what we get to the answer x plus y.
Yeah.
X plus x.
Yeah, I would add in a not X column. When I do it, that's what I do. Add in a not X column on its own. And that way, yeah, it's a little easier to just compare.
However far you want to take it will work. Questions? Here's where it starts to get more interesting. De Morgan is counterintuitive, but we proved with truth tables that it works. It's got two forms. X or y bar over it is the same as x naught and y naught. And if I were to give you this and say prove that, how would you prove it?
Truth table?
Just draw the truth table. Draw one truth table for x or y naught. Draw a second truth table for x naught and y naught, and show that they have exactly the same answer, the same solution. The same thing is true with De Morgan's other equation, is that x and y, the quantity naught, is the same as x naught or y naught. Like I say, these are not intuitive, but they're true. And you can prove them to yourself, prove them to me if I ask for them, with a truth table. In fact, if I were to ask something like this on the test, I would say prove this De Morgan's theorem using a truth table. I'd let you go to town. Okay. I'm going to stop right here for a moment. Okay, this is going to be a second recording, and it'll take me a couple hours to get it to save as an MP4, but I'll get them both posted to Canvas so that you can get to them.
Yeah, I was about to say, one big video file, it's gonna take forever to upload.
It's going to be 2 files. It'll still take forever to upload.
Yeah.
It'll take half a forever.
Oh, it's 2 files. Oh, yeah, no.
Just find yourself a place where you got a fast enough internet.
It'll be as fast as if they're rendering a 3D animation.
Okay, so let's begin. One of the important details we looked at was that in industry, we can create any fundamental gate we want from either a NAND gate or a NOR gate, or a combination of NAND gates and NOR gates. This gets to be very helpful when we realize that a single 16-bit chip or 14-bit chip has 4 gates on it. So we can use, for example, 2 gates or 1 chip to take this and create 2 NAND gates to create X equals AB. We can take 1 chip with 3 of its gates to show that A and B into 3 NAND gates can create A or B. We can take a single chip and just both inputs to the same source invert, and we've got the inverter. So we've got the inverter, we've got the AND gate, we've got the OR gate using just NAND gates. Similarly, we can do the same thing with OR gates. Connect both inputs to the same pin, invert, we've got A to not A. There's our inverter. We could do it A, B, inverted again, and we get A or B. So we get the OR gate function. We can get the AND gate function again using 3 gates, 3 NOR gates, and it's just a matter of how we wire them.
In the test, do we have to know either way?
Say again?
In the test, do we have to know either way, like you're going this way or that way, or from this way?
I could take it either way. I could say create an OR gate out of NAND gates. I could say create an AND gate out of NOR gates. So that's feasible. The form of equations becomes very important, and I'm not going to focus on the product of sums. I'm going to focus just on the sum of products. The sum of products means I have a product term ORed with another product term. So this is the sum of 2 product terms. This becomes the sum of 4 product terms, sum of 5 product terms, but they're all sum ORed as the output of AND gates in some form. The other form is the product of sums. You could multiply this through using the distributive law, and by multiplying it through, you've just converted it to a product of, or a sum of products. So I'm not going to do anything with the product of sums form. But the sum of products works very nicely with what's called a Carnot map or K-map. We spent a good bit of time looking at K-maps this semester because they help you simplify a circuit so quickly. If we look at this input and this output, if I know that A is 0, B is 0, but the output's a 1, then I've just calculated that the output is A naught and B naught. I look down here. If A is 1 and B is 1, then the output is AB. Well, I take these terms on the truth table, and I know I've got 2 terms to deal with, A and B, and I've got both A and its complement. So I come over here and I create a table. A naught, which is 0, B naught, which is a 0, A, which is a 1, B, which is a 1, and I look for the spots where I know that A naught, B naught is a 1, and I'm going to put the 1 in this table to show that it is a 1 under those conditions. Similarly, I'm going to take A, B. I know that that product is a 1, so I'm going to put a 1 in that square. And this becomes my Carnot map for this expression. This one has no simplification that fits where our conversation's going, but this shows how to create a Carnot map. We look where the truth table has 1s, and this is where A is 0 and B is 0. So A is 0 and B is 0 here. So I'm going to put a 1 there. When A is 0 and B is 0, I get a 1 out the truth table. In this case, when A is 1 and B is 1, I get a 1 out of the truth table. That's the beginnings of Carnot mapping. So now I take a much more extended expression. I've got 4 inputs to this Carnot map, and I can see that I've got an output of a 1 when A, B, and C are 0s, but D is 1. So I come over and I find that spot. A and B are both 0s, C's a 0, and D's a 1. That lets me put a 1 in this square. It corresponds to A being 0, B being 0, C being 0, and D being 1. So that's this term. Then I come down here to the next one. I've got A is a 0, B's a 1, C's a 0, D's a 1. So I've got a 0, 1. Okay, that's this row. And I've got 0, 1 as my column. That's this column. So this 1 is going to go here. A's a 0, B's a 1, C's a 0, D's a 1. Then I come down and I find the next one. A and B are both 1s, C is a 0, D is a 1. A and B are both 0s, comes up here. No, I'm sorry, A and B are both 1s. Both 1s is going to be this row. And now I want C is a 0 and D is a 1. C is a 0, D is a 1. I put a 1 in this column. The last one I'm looking at is A, B, C, D. They're all 1s. A, B, there's 1, so that's this row. C, D, that's this column. So the intersection's here. So now I have 4 cells that have 1s in them from the truth table. Notice also how I counted. A naught, B naught, A naught, B, A, B, A, B naught. In other words, 0, 0, 1, 0, 1, 1, 1, and 1, 0. What code does that sound like? Go back to gray code.
Oh.
I'm only changing one bit at a time between these cells. But from this, what can I see? I can see that when A is 0, I can hit both of these cells. B or B naught, that's B's changing, C naught's changing, and C naught's not changing, D is changing. So what have I got? I've got A naught, C naught, D, 3 terms that describe these 2 cells. I come down here to these 2 cells. They're in a row together. I know this is AB, but C's changing, but D's not changing. So this is ABD. So my final expression becomes A naught, C naught, D, or ABD. And there's the simplification of this one. Anytime I've got adjacent 1s, So even on a 4 ABC, if I got two adjacent ones here, then I can say that this is A not B. It doesn't matter what C is, I still got a 1 out.
Yeah, they cancel each other out.
Yeah, the C's cancel each other out here. In this one, I've got A not B, AB, so the A's cancel each other out, to use your term, and I've got a B, C not. Talk about these two. I can come around and I can notice that I can loop around top and bottom. A naught, B naught, C naught describes this one. A, B naught, C naught describes this one. A's changing, but I've got B naught, C naught describing these two. I can wrap it around the ends too and accomplish the same thing. Technically, on this one, I could wrap it top to bottom, but I haven't gained anything. Because I still have to deal with this one, and I still have to deal with this one. So the simplest expression becomes, looking at this one, A naught, B naught, C, and this one becomes A, B naught, D naught. If I've got 4 together, it's even more fun. C can do whatever it wants, D can do whatever it wants, but I've got AB covering all 4. Under that rare occasion that I build a 4x4 and I find out that the first column and the second column are 1s, what I find out is that C naught, D naught, C, D naught, D naught's a common term, but A changes and B changes, so the solution to this one is merely a D naught term.
Because the C's cancel out.
Mm-hmm. Yep, C naught in the first column, C in the fourth column. So the C's cancel.
And all the ABs cancel because of what?
Okay, A naught, A. So A naught and A cancel.
Yes,
B naught and B cancel.
yes.
So all I'm left with is C naught and D naught in this column, and C and D naught in this column. C and C naught cancel. So all I'm left with at the end is D naught. Exclusive OR, exclusive NOR. This was a fun one. Exclusive OR. If A and B are both 0, then the outputs is 0. If A and B are both 1, the outputs is 0. If A is 0, B is 1, I get a 1. If A is 1 and B is 0, I get a 1. What does this mean? This means that as long as I get a 1 out, as long as A and B are different. That's the exclusive OR. Truth output expression, A not B or AB not. And there's the solution.
So that's exclusive.
This is exclusive OR.
Oh. Just as like, okay. That's a representation of the one symbol of
Right.
exclusive.
Here is the exclusive OR symbol, which is A not B or AB not. And we have the plus sign with a circle around it to show this is the key. Exclusive OR. Exclusive NOR is just the opposite. If A and B are the same, I get a 1 out. 0, 0, I get a 1. 1, 1, I get a 1. If they're different, I get 0 out. So it's AB or A not B not. As long as A and B are both the same level, I get a 1. Exclusive NOR is the same as exclusive OR, but with the inversion symbol. I can come up with a circuit where I take two numbers. X1 is going to be compared with Y1. X0 is going to be compared with Y0. And as long as they are the same, I get a 1 out. So 0 and 0, 0 and 0, I get a 1. I look at it again, 0 and 0, 1 and 1, I get a 1. 1 and 1, 0 and 0, I get a 1. And then finally, if they're all 1s, 1 and 1, 1 and 1, and I get a 1. So here's a truth table to prove the exclusive OR circuit. We also, and you did this as a lab, enable and disable. If I've got an AND gate and I want the data from A to go to the output, then I put a control lead on B. The control lead on B says if B's a 1, then whatever's at A gets communicated through. If B's a 0, then whatever's on A gets turned off because the output is a 0. So B's my control on this one. I can do it with a NOR NAND gate, but recognize the inversion of the signal. If B's a 1, then this is a 0 out. If this is a 0, then whatever's on A is going to be communicated through, but inverted.
Oh, you're just basically saying like a carry.
Huh?
It's like a carry.
No, we're not looking to carry here. This is a control. This is a switch, on and off.
Oh, gotcha.
If I put a 1 here, then whatever's at A is just shorted to ground, it's turned off. A 1 here puts a 0 here. With an OR gate, I'm going to put a 0 here, and whatever's on A goes through. If I put a 1 here, I'm going to get a 1 out. And finally, the opposite. If I put a 0 here, that's going to put a 1 out. If I put a 1 here, then whatever's on B is going to come through, but it'll be inverted. I can do the same thing with the disable circuits. Same process. If I make B a 0, I've just shut off the output. If I make B a 0 here, the output goes to a 1. Doesn't matter what's at A, the output's at 1. The OR gate, if B's a 1, then the output's at 1. Doesn't matter what's at A. In this case, if B's a 1, then the output's a 0. And again, it doesn't matter what's at A. So if I put the pairs together, B's a 0, then the NOR gate's going to give me an inverted output. If B's a 1, I block it. These are great digital switches. If I've got a circuit where I want to control A, then I have two separate inputs, B and C. B and C both have to be high to get an output. If B is a low, what's the output? 0. If C is a low, what's the output?
0.
But if B and C are both high, what's the output?
Depending on what A is.
It depends totally on what A is. Explicitly on what A is. We can do the same kind of enable, disable using the exclusive NOR gate where they have to be the same or they have to be different. Otherwise, that's how we control what comes through this OR gate. I can do the same thing with with an AND gate and inverter. And again, if A is a 0, then I get whatever's at B. On this one, if B is a 1, then I get whatever's coming in A. Or if B is a 1, it's locked, because that's always a 1. Or that goes to 0, this goes to 1. If B is a 0, then this is a 1 here, and whatever is coming in at A is going to be clocked through. So again, a whole bunch of creative ways to to allow a signal through or not allow a signal through.
Is the circle supposed to be on the left side of the inverter?
What difference does it make?
I don't think it made a difference, but I'm just so used to seeing it the other way.
We're so used to seeing it the other way, but it means the same thing.
I mean,
That's a real good question.
Yeah.
Does that look familiar at this point? Yep. Enough said about this slide. Same slot or same chip, looking at it, look for the notch, look for the dot, and that tells you where pin 1 is. And then we go down one side, 1 through 7, swing over to the other side and count 8 to 14. And in most of these, pin 7 is ground and pin 14 is hot. Not on all of them, as you saw with a couple circuits you built. Now this is showing in American measurements, SAE. In metric, this is 0.3 inches, and this is 0.1. I'm sorry, 0.3 millimeter. 3
3 centimeters?
No,
3 millimeters? No.
I think it's 30 millimeters.
Oh.
And no,
No, it's 3 millimeters.
that would be 3 millimeters and 1 millimeter.
That's right.
I mean, yeah, it's like 3 of the spaces.
But these were designed with metric sizes. We have talked with this as recently as last class period. A 1 is a 1, a 0 is a 0, except that a 0 can be up to 0.8 volts.
Oh, yeah.
And the 1 can be as low as 2 volts. I can't do any analog to digital conversion based on logic outputs. I've got to absolutely have, or I have to have a stable external source providing the value that I want to encode. But that also says, as long as it's not in this intermediate indeterminate zone, I know if it's a 1 or a 0. The only thing that's going to load this into the indeterminate zone, if it's a 1 and I've got too many chips that I'm trying to drive, and I'm putting current into too many chips, then I may not be able to put out enough voltage to get this above 2 volts.
Oh, I see what you're saying.
What is happening in that in the area?
Indeterminate,
Yeah, what's happening?
it doesn't know whether to treat it as a 1 or a 0.
It just lost kind of.
It'll be depend on the noise in the circuit.
It's like
Generally, it'll float to a 1, but I can't promise that.
They'll do something.
it's unpredictable.
It'll do something and you can't be sure.
And you don't want unpredictability in circuits.
Latches. Boy, did we have fun with latches.
Yeah.
I'm going to stick with just the NAND latch as a latch. We had, well, 2 NAND gates cross-connected, cross-coupled, so that the Q of 1 is the input to the second stage, and the Q naught becomes the Q naught becomes the input to the first stage. In this case, when I put a negative pulse here, that's the set that puts the output high. When this goes high, and this is already high, then this is going low.
It's almost like, all right, we're still going. You stay put right there.
Exactly. But the output sets the input to the second stage, and we're dependent on the external pin. So the two stages work together. The reset works just the same way. We hold the one at set, and this, normally this is all working on inverted logic, where a 1 is static and 0 is going to be the change. So if this is typically a 1 and this is a 1, there'll be no change. But if this is a 1 and this goes to 0, that 0 is going to force this to a 1. The 1 here, 1, 1, that forces Q to a 0. And that's the latch.
So the set and reset cannot be 0.
Say that again?
Set and reset cannot be 0.
Set and reset cannot both be 0. That's correct.
Yeah, that's the-
They must both be at 1, or one of them can go to 0 and the other stays at 1. The NAND gate does the same thing. We'll keep trucking through here. Take a look at these circuits. This was one where we had the ability to clock it so that set and reset have to be stable when the clock hits to decide what goes out at D. If set is 0 and reset is 0, then on this case, the rising edge of the clock, how do I know this is a rising edge clock?
There's no dot in front of the clock.
No dot in front of the clock.
it's not inverted.
So on the rising edge of the clock, no change. If set's a 1 and resets a 0, then Q is going to go to a 1. If sets a 0 and resets a 1, then on the clock it's going to go to a 0. Notice that the output follows the set pin. But if set's 1, resets 1, flip a coin.
Like a invalid, right?
Can't trust it.
Like a invalid. If it's both like a set and reset, you press it.
Yeah, it doesn't go.
Like it's go wrong or it's go crazy.
Yeah.
If it's set and reset.
I would have it go-
Same thing here if I'm dealing with the inverted clock. It's when the clock is low that I communicate what's at the set to the output. So that if set is 0, reset 0, no change. Set is 1 on the clock, Q goes to 1. Set is 0 on the clock, Q goes to 0. That's exactly the same as we saw here, just the clock direction makes a difference. The data set reset Q is the same.
Oh, so that's obviously determines if the clock is going down or up.
You're looking for the bubble.
The ball.
That's
yeah.
good down.
Yeah. If it has the ball, it's going down. If not, then it's going up.
Yeah.
Yep. This is the actual circuitry inside the flip-flop. Let's not worry too much about that. This was also a good area. We've got set and preset and clear. It's a JK flip-flop, which means that the J and K follow Q. Is this rising edge of clock or falling edge clock? Falling, okay. If J is 0 and K is 0, then on the clock, no change. If J is a 1, K is a 0, on the clock it stays a 1. Here it goes to 1. If J is a 0 and K is a 1, on the clock, Q goes to 0. The difference with a JK flip-flop is that when J is a 1 and K is a 1, it switches state.
I know this is simple, but I just realized when it's going down, you look at the down part of the wave. I just realized that.
Yeah. Yep.
I was confused about that before. Okay,
That's part of the reason we go back over it a couple weeks later.
thank you.
In this case, on the clock, this is going to function just like a JK flip-flop. But if set and preset and clear are operational, if they're both ones, it means nothing's happening. If they're both zeros, you wired the circuit wrong. But if one's a 1, if preset's a 1 and clears a 0, preset's a 1, clears a 0, then we are going to put a Q to a 0. If preset's a 0 and Q's a 1, we're going to, excuse me, preset's a 0 and clear is a 1. That 0 is going to force us to a preset and put Q to a 1. Remember, this is active on a 0. The 0 forces the action, not the 1. There was a variation of this on the last test. I changed the waveforms for the preset and the clear, so the Q is going to be different, but I gave you essentially the same. J and K are held at 1, and clock is held at clock. You notice that this is a negative going clock, so the changes are going to be on the falling edge of the clock. This would be one worth taking a look at as you study for your test. We talked about adders. This is where we got into the last part of the semester. We're going to take two inputs, A and B. A, 0 plus 0 is a 0. Carry is 0. No big deal. If A is a 0, B is a 1, 0 plus 1 is a 1.
Yep.
Carry is 0. I mean, this is second grade math, right? 1 plus 0 is a 1. Still got no carry. 1 plus 1 is a 0 in binary with a carry of 1. So this numerically would look like a 1-0 when you wrote it down. Create the Carnot map. With the Carnot map, the sum 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is a 0, but I'm going to carry the 1. When you turn that into a schematic, what do you got? You got an exclusive OR on the sum. They can't both be the same. If they are the same, it's a 0 out. And the carry is only if both are 1s. Two AND gates. On these, you started building circuits. And you built the circuits to accomplish these. This is the one you had most of the fun with, the ripple counter. J and K are our inputs. Notice the note. All of the J's and K's are 1s. What does that mean? On a JK, if they're both 1s on the clock, it toggles.
So values go down, it's toggle. When the clock goes down, it's toggle.
When the clock goes down, it toggles. This one has to clock twice to get clock once over here. This has to clock twice to clock once over here. This one clocks twice to get clock once over here.
1, 2, 4, 8.
Exactly, 1, 2, 4, 8. That means that it takes 16 cycles of the clock to get back to 0. To count all the way around. You proved that. You did it. Some of you had some real fun times building your circuits. But this sets a number. This sets the mod number. How many cycles before the output goes back to 4 zeros? And in this case, if they started at 0 A0, B0, C0, D0. We don't have all of them at 0 until we reach the 16th clock, at which point they drop down. So what mod is this counter?
Mod 16.
Mod 16. And you learned in lab how to do that as a mod 10 and a couple other things. So there's the mod number. How many states does the counter go through before the system recycles? Not going to worry about propagation delay. If you start running them fast, they get noisy and get into trouble. Here's where we added 2 AND gates in order to make the whole thing synchronous. That would put 1s on J and K and all the clears. When A switched, it fed up to B. Or A fed B, A also fed C and D.
Also preset can be a 1, 2, right?
This is not the preset. This is to make so that D and C and B and A are all switching at the same time. You did the up counter, you did the down counter. The last circuit you did in lab was the up or down counter. And you had the numerical count showing up here in the top right corner. But only when all of these inputs are high can we get it to toggle. J and K have to be 1 here to toggle. J and K have to be 1 here to toggle coming from A and B. This one's A, B, and C to allow this one to toggle. A's going to toggle to B, but this ends up being exactly the same delay no matter how many flip-flops we add in because of these AND gates that make sure they all synchronize up. The mod 10 counter, you set this up so that when the output was a 10, a 10, which 10 decimal is a 1010, right? So, reading that, B is going to go to a 1, D is going to go to a 1, 1, 0, 1, 0. When B and D are both 1s, that's a 10, and that sets the clear line. You had a hard time with it until you figured it out, and all of a sudden it made sense. The last thing you did was the up-down counter. Oh, I didn't bring the up-down counter in. I just showed the down counter. What did we change for the down counter?
We took input from the
Presets.
No. What made the difference?
all the logic is driven off of the Q naught.
The logic is driven off of the Q naught line for the down counter. So we take A naught, B naught, C naught, and D naught, and they ran the down counter. And guess what, guys? We've just reviewed this system, the whole semester.
Nice. Pretty quick.
It was quick. You've got this complete set of notes available to you. You've got the tape, the audio tape is going to be, or I say audio, the presentation is going to be available as 2 files. So, and the test will be open book, open notes. No open computers. Questions?